So we have already done looking at several example calculation of normal shock wave. So we are now approaching our last the second last subtopic, which is measurement of velocity in a compressible flow. Right. For incompressible flow, the velocity can be obtained from a knowledge of both the total pressure and the static pressure of a pitot tube at a point, right? So this is for incompressible flow, okay? However, in the compressible flow, and both subsonic and supersonic, if we consider the Mach number rather than velocity, a knowledge of the pitot pressure and static pressure is sufficient to calculate Mach number, although the formulas are different for each Mach number regime. Just to remind ourselves, the regime of the speed over here, low subsonic, less than 0.3, where it is incompressible. High subsonic, you have a region of 0.3 to 0.8, where this is a compressible flow. Transonic, okay, this is the flight regime. Supersonic, more than 1.2. Hypersonic, more than 4. So let us look into what are the measurement of velocity for incompressible flow. This is just a revision, how a pitot tube looks like on the ground, and then this is the pitot tube used on a typical aircraft that being fixed on the wing. So this is just example on the wing. Some a pitot tube on the subsonic aircraft, or like a normal jetliners, 737 or A320 or any other bigger aircraft, they have the pitot tube very near to the nose of the fuselage, nose of the aircraft. All right. So if we look into the technique, okay, the pitot tube, how does it work? Okay, so this is just a revision. P total equal to P static plus P dynamic. So you can then rearrange to get the P dynamic and dynamic pressure to become the half rho V squared, and where basically what is P static? Pressure you feel by moving with the flow at its local velocity. The total pressure is basically the pressure that the flow achieves when velocity is 0, and the dynamic pressure basically sometimes called the velocity pressure, anyway we have the kinetic energy element, which is increased in moving pressure over its static pressure due to motion. So to find the velocity of the aircraft, basically you use Bernoulli equation, solve the Bernoulli equation, you will then get the value of the velocity from the corresponding value of the total pressure minus the static pressure divided by the density times 2 to the square root. All right. So just a reminder for ourselves. Now let us look into the compressible flow problem, measurement of velocity in a compressible flow. Okay, so imagine you have a subsonic flow, okay, subsonic compressible flow. So you have the mouth of the pitot tube at point B, right? Pitot pressure is the free stream total pressure P01. Hence, a fluid element moving along streamline AB. So from A to B, where A is a stagnation, the point B is a stagnation region. Point B is a stagnation region, okay, and which is then the flow travel streamline AB is brought to rest isentropic at point B. So in turn, the pressure sensed at point B is the total pressure of the free stream. P01 is over here. So this is the pitot pressure read at the end of the tube. If in addition, we know the free stream static pressure P1, okay, then the Mach number in region 1 can be obtained from the equation that we have already looked earlier, okay. So for this case, we can write equation into the expression of P1 over P1, right? So and solve for M1 squared we can then get this expression. So clearly, from the equation, the pitot pressure P1, and the static pressure P1 allow the direct calculation of Mach number. So you can then directly get the corresponding value of the Mach number. All right. Then the flow velocity can easily be obtained from the equation where we recall M1 equal to U1 over A. So we rearrange the expression for the velocity squared, and we will get the value. Clearly, unlike incompressible flow, a knowledge of the P01, pitot pressure, and the P1 is not sufficient to obtain U1. Okay, so we also need the free stream speed of sound A1. Okay, we have to find A1 over there in order to measure the air velocity. All right. For supersonic compressible flow, where in this case we have a normal shock wave, right? And the mouth of a pitot tube at point E. Okay, we imagine you have a shock and a vehicle or aircraft traveling at a supersonic speed, right? Where you have a pitot measurement over there. So at point E, it is at stagnation region. The fluid element moving streamline from C to D to E, crossing the normal shock, right? Okay, is brought to rest at point E. However, because the free stream is supersonic and the pitot tube presents an obstruction of the flow, there will be a strong bow shock in front of the tube. Okay, that's what happened. So, hence streamline the CDE crosses the normal portion of the bow shock. So, a fluid element moving along streamline CDE will be first decelerated to non-isentropic to a subsonic velocity at point D, right? And then it is isentropically compressed to zero velocity at point E, right? As a result, the pressure at point E is not the total pressure of the free stream, but rather the total pressure behind the normal shock wave, because we have the normal shock wave. Okay, and we basically it's behind normal shock P02, and keep in mind that because of the entropy increases, S2 minus S1 is more than 0 across the shock, there is a loss in total pressure across the shock where P02 at this point is less than P01 before the shock. Okay. However, knowing P02 and the free stream static pressure P1 is still sufficient to calculate the free stream Mach number M1. All right, so you can get it as follows, where P02 over P2 is the ratio of the total pressure to static pressure in region 2 immediately behind the normal shock, which is over here. And finding the P2 over P1, which is the static pressure ratio across the shock. So you can use this expression, okay, and finding the equation of Mach number, using equation of Mach number. So you can then also use the equation of pressure ratio between the shock wave. All right. So substituting all the previous equations into pressure ratio, and after some algebraic simplification, right? So you can then get this expression, and this equation is called the Rayleigh-Pitot tube formula. It relates the pitot pressure P02 and the free stream static pressure P1 to the free stream Mach number M1. So look at the equation M1 as an implicit function of P pressure ratio P02 over P1. And for convenience, in making calculation, the ratio of P02 of P1 is tabulated versus M1 in a graph, right? So let us look into an example, all right? A pitot tube is inserted into an airflow where the static pressure is 1 atm. You have to find the flow Mach number when the pitot tube measures at three different conditions. One is at 1.276 ATM, and then 2.714 ATM, and finally 12.06 ATM. So first we must assess whether the flow is subsonic or supersonic. Okay, at Mach 1, the pitot tube would measure to be P naught over P, the pressure ratio at 0.5 to 8, which is equal to 1.893 P. Okay, hence P naught less than 1.893 ATM, and the flow is subsonic. When P naught above 1.893 ATM, the flow is supersonic. So you can now know that which one is a subsonic condition and which one Mach number when pitot measure which is more than which is supersonic. All right. Condition A, pitot tube measurement 1.278 ATM. So the flow is subsonic, right? Because it is less than 1.893. So hence the pitot tube is directly sensing the total pressure of the flow. So you can immediately from Appendix A, P naught over P, which is equal to 1.276. Okay, for 1.276 P naught over P, you will get a Mach number of 0.6. All right, and for pitot tube measurement 2.714 ATM, and the flow is already supersonic, right? So the pitot tube is sensing total pressure behind a normal shock wave. So you look at Appendix B instead of Appendix A. So look at Appendix B for the pressure ratio of 2.714. You will read the value of M1 to become 1.3 Mach number. And finally, for pitot tube measurement to 12.06 ATM, right? It is a supersonic. You can now also go into Appendix B at pressure ratio of 12.06, which read Mach number of 3. All right. Another example over here. Consider a hypersonic missile flying at Mach 8, right? At an altitude of 20,000 feet, where the pressure is 973.3 pounds per square feet, right? The nose of the missile is blunt, right? Similarly, like shown in this figure. So calculate the pressure at the stagnation point on the nose over here. Examining the blunt body in this figure, the streamline that impinges at the stagnation point has traversed the normal portion of the bow shock wave. By definition, the velocity at this point is known as stagnation point. So it is a V equal to 0. So since the flow is isentropic between the shock and the body, basically what happened between this bow shock and the nose of the missile, right? Okay, the pressure at the stagnation point on the body is total pressure behind normal shock with an upstream Mach number of 8. And let us denote the pressure at the stagnation point as PS, right? So since P02 is total pressure behind normal shock, then PS is equal to P02, right? So from Appendix B, looking at Mach 8, you get the pressure ratio to become 82.87, right? So hence, finding the stagnation pressure PS, which is equal to P02, you will then get the value of 8.0710 times 10 to the power 4 pound per square feet. And since 1 ATM equal to 2,116, then you get the PS, the stagnation point, to become 38.1 ATM, right? So note that the pressure at the nose of the missile is quite high, 38.1 ATM. And this is typical of hypersonic flight at low altitude. So when we check on the calculation, this problem can also be solved by first calculating the upstream total pressure from Appendix A. And then using total pressure ratio across the normal shock from Appendix B. So if we go through via calculation using Appendix A at Mark 8, the pressure ratio is given here, 0.9763 times 10 to the power of 4, right? You will then get the pressure at P01 to become 9.502 times 10 to the power of 6. Then, looking at Appendix B for Mark 8, right, you get the pressure ratio 8.8488 times 10 to the power minus 2, right? And then you will find the PS to become 8.07 times 10 to the power of 4, which is the same. You can have a different approach of finding the solution. Okay, our very last example for measurement of velocity in a compressible flow. Consider the Lockheed SR-71. I believe most of you, maybe all of you, have already looked at this particular popular aircraft. Okay, this is a Lockheed Martin, or known as the Blackbird. So normally it's being flown at an altitude of 25 kilometer, and the pressure measured by a pitot tube on this airplane given a value of 3.88 times 10 to the power of 4 Newton square meter. You have to find what is the velocity of the airplane by just using the pitot tube value. All right. Now, looking at Appendix D, why we want to look at Appendix D? Because it mentioned 25 kilometer, right? As at Appendix D, at 25 kilometer altitude, you then read the corresponding pressure value and the temperature, right? So you can now obtain the pressure ratio of 3.88, which is already read by the pitot tube just now, divided by P1 at 25 kilometer altitude. So you get the corresponding pressure ratio. Then use this value of pressure ratio to look into Appendix B and find the corresponding Mach number. All right. So if we go to Appendix B, right, go to Appendix B and find P pressure ratio of 15.35. We go to Appendix B now, right? So we want to find 15.35. 15.35 pressure ratio, 15.35, right? So we go pressure ratio 15.35. Okay. Okay, this is 1.5. We go a bit down, right? Pressure ratio. Oops. Right, I think this is about here, Okay, so we have a Mach number of 3.4. Where is it? 3.4. This one. Okay, 15.35. So you have a Mach number of 3.4. All right. So you then calculate the speed of sound to become 295 meter per second. So thus the velocity, putting the value of the Mach number and the speed of sound, you get it to be traveled at 1003 meter per second. Okay, so we are already completing all the examples in relation to the normal shock, and let us go into the summary and just to recap back of what we have already gone through so far in the past 3 lectures, from lecture number 3, lecture number 4, and today is lecture number 5. So basically we have already looked into the speed of sound in a gas, which is given as this expression. If you look at Anderson, it is equation 8.18, for a calorically perfect gas. So you can now use this expression where we have the pressure times the gamma, as well as that the density, or you can then use the popular speed of sound expression, the square root of gamma RT. The speed of sound depends only on the gas temperature, right? So you want to find the speed of sound, so you just use square root of gamma RT, all right? For a steady adiabatic inviscid flow, the energy equation can be expressed as the enthalpy and the velocity. So you have H1 plus U1 squared over 2, which is equal to H2 plus U2 squared over 2, and where we know already H equal to CPT, where CP is the specific heat capacity at constant pressure times the temperature, right? So you can express the energy equation. So this is known as the energy equation. Next, by knowing the value of the earlier CPT, where you can then rearrange the value by having the speed of sound inside the equation, right? So we have equation 832, 833, and 834, all right? So total conditions in the flow, which are related to static conditions via this expression CPT plus U squared over 2, which is equal to CPT naught, right? And you can also have the temperature ratio expression of a Mach number, the pressure ratio expression of the Mach number, as well as the density ratio expression for the Mach number. And note that the ratios of total to static properties are a function of local Mach numbers only, and these functions are tabulated in Appendix A for isentropic flows properties, right? And then for normal, so basic normal shock equations, we have the three equations: continuity equation, expression 8.2, momentum equation, expression 8.6, energy equation, expression 8.10. And these equations lead to relations for changes across a normal shock as a function of upstream Mach number M1 only. And so you can use this expression to find the value of M2 by subjected to the availability of, you have to first to calculate the value of M1, all right? Okay, to continue, you have the density ratio value, the pressure ratio value, and then you can get the values expressed in terms of the temperature ratio and the enthalpy ratio, right? So this is the entropy conditions, right? And another expression 8.68 and 8.63, where this lead to the normal shock properties, which are tabulated versus M1 in Appendix B, right? So, for example, like you are finding a condition of Mach number, you can then get the corresponding pressure ratio, corresponding density temperature ratio, and corresponding M2, all right? For a calorically perfect gas, and the total temperature is constant across a normal shock wave, and this is our assumption that T02 equal to T01, because it is constant. However, there is a loss in total pressure across the wave, and the pressure will be reduced when the flow crosses the normal shock wave, right? For subsonic and supersonic compressible flow, and the free stream Mach number is determined by the ratio of pitot pressure to free stream static pressure. However, the equations are different. For subsonic flow, it is expressed as equation 8.74. For supersonic flow, you can find the values to be obtained from this expression 8.80. So as I said earlier, these equations are normally being used, and you can use it normally being given, so you do not have to memorize the most of the equations. All right, as long as you since you do not have to memorize, you must ensure that you know which equation to be used, which table to refer to, especially Appendix A and Appendix B. At the same time, if it is require you to look at Appendix D for the values at different altitude, right? Because it requires different pressure and also different value of the temperature and density. If the aircraft traveling at a different altitude. So with that, that wraps up our topic on normal shock